40 light-years from Earth, there are 7 planets. All of them are approximately the same size as ours. All of them are rocky. All of them orbit the same star, a small, dim, ancient red sun that has been burning for longer than our solar system has existed. And 3 of them sit in the region of space where the temperature is just right for liquid water to exist on a planetary surface. For as long as astronomers have been searching for life beyond Earth, they have been looking for exactly this: rocky planets, right size, right temperature, orbiting a stable star, close enough to actually study. They found all 7 at once in 2017, and the announcement stopped the scientific community in its tracks. Since then, NASA's James Webb Space Telescope, the most powerful observatory ever built, has been observing this system with a focus and dedication unlike anything in the history of exoplanet science. One planet at a time, year by year, working through each world in sequence, pointing its golden mirror at a star 40 light-years away, and reading the light that filters through each planet's edge as it passes in front of its sun. The results have been stranger than anyone predicted. Some of what Webb found was sobering. Some of it was unexpected in the opposite direction. And the most important planet in the system, the one sitting deepest in the habitable zone, has just been observed for the first time, and the answer is not yet clear. This is the story of what James Webb found in the TRAPPIST-1 system, and why what it is finding may be the most important scientific work currently happening in astronomy. This is Deep Space Declassified. New classified file every week. Subscribe before we go further. Let's get into it. February 22nd, 2017. A press conference at NASA headquarters in Washington, D.C. that the scientific community had been anticipating for weeks. The announcement was this: astronomers using the ground-based TRAPPIST telescope in Chile, supplemented by NASA's Spitzer Space Telescope, had confirmed the existence of 7 Earth-sized planets orbiting a single star called TRAPPIST-1, located approximately 39 light-years from Earth. 7 planets. Not 2, not 3, 7. All of them rocky, all of them with estimated sizes and masses close to Earth's. And remarkably, 3 of them orbiting within the star's habitable zone. The reaction in the astronomy community was immediate and, by the measured standards of scientists, unusually enthusiastic. The closest analog to our own solar system ever found at that point. The best collection of habitable zone rocky worlds ever assembled around a single star. Planets close enough around a star small enough that the James Webb Space Telescope, then still being assembled and tested, might actually be able to study their atmospheres in detail. TRAPPIST-1 immediately became the primary target for the most important question in astronomy: is there life elsewhere? Understanding why this system was so significant requires understanding 2 things. First, what the TRAPPIST-1 star actually is. And second, what transmission spectroscopy, the technique Webb uses to study planetary atmospheres, actually does. TRAPPIST-1 is a red dwarf, a small, cool, dim star containing only about 8% of the Sun's mass, right at the lower limit of what qualifies as a star rather than a brown dwarf. It is ancient, estimated at approximately 7.5 billion years old, 3 billion years older than our own Sun. Because it is so small and so dim, the habitable zone around TRAPPIST-1 sits extremely close to the star. All 7 planets orbit within a region smaller than the orbit of Mercury around our Sun. The entire TRAPPIST-1 planetary system, all 7 planets, and all their orbits would fit inside the distance between our Sun and its closest planet. This compactness is what makes the system observable. The planets orbit quickly. TRAPPIST-1e, the most prominently habitable candidate, completes a full orbit in just 6 days. Faster orbital periods mean more transits, more opportunities for James Webb to catch each planet crossing in front of its star and take readings. When a planet transits its star, a tiny fraction of the star's light passes through the thin sliver of the planet's atmosphere, if it has one. Different molecules in the atmosphere absorb different wavelengths of that light. Webb's near-spec instrument, the near-infrared spectrograph, is sensitive enough to detect those absorption signatures. By analyzing which wavelengths are missing from the light that passes through, astronomers can identify which molecules are present: water vapor, carbon dioxide, methane, oxygen, in theory, if there is an atmosphere to absorb the light in the first place. In the TRAPPIST-1 system, that question has been the central one since 2017. Do these planets have atmospheres? And Webb was built, in part, to answer it. The 3 habitable zone planets in the TRAPPIST-1 system, designated E, F, and G, are the ones that have captured the most scientific attention. But Webb did not start there. It started with the inner planets, the ones closest to the star, where the environment is harsher and the answers might come faster. TRAPPIST-1b, the innermost planet, orbiting less than twice the distance of our moon from Earth, was the first target. In 2023, Webb measured its thermal emission, the infrared light the planet radiates as heat. The result was stark. The planet's dayside temperature matched what you would expect for a bare rock with no atmosphere to distribute heat, approximately 230 degrees Celsius. An atmosphere would moderate that temperature. A thick atmosphere would redistribute heat and make the dayside cooler. TRAPPIST-1b showed no such moderation. The conclusion, TRAPPIST-1b almost certainly has no significant atmosphere. Bare, baking, airless. TRAPPIST-1c came next, also close to the star, also receiving intense radiation. Webb measured its thermal emission and found similarly high temperatures. When astronomers looked for evidence of a thick carbon dioxide atmosphere, a scenario that would have been detectable even from this distance, they found none. TRAPPIST-1c appeared to be another world with minimal or no atmosphere. TRAPPIST-1d followed and produced similar results. 3 planets, 3 disappointing readings. The 3 innermost worlds of this celebrated system appeared to be rocky, airless planets baked by a star whose radiation had stripped away whatever atmospheres they might once have had. But then something unexpected happened. In December 2024, researchers at the Max Planck Institute for Astronomy in Germany published new Webb observations of TRAPPIST-1b, the same planet that Webb had already seemingly ruled out as having an atmosphere. The new measurements, using a different observational technique, produced temperatures that did not fully match the bare rock prediction. There was more variation in the temperature readings than a completely bare planet should show. The planet's night side, which should be cold and dark on an airless world, appeared slightly warmer than expected. Warmer than expected. On a planet that was supposed to have no atmosphere to carry heat around. The Max Planck team was careful in their conclusions. The data was not yet sufficient to confirm an atmosphere, and there were multiple possible explanations for the temperature anomaly. But the December 2024 paper explicitly stated that a thin, volcanic outgassing atmosphere could not be ruled out. Webb's earlier conclusion about TRAPPIST-1b, no atmosphere, had been questioned by Webb's own subsequent data. This is not a contradiction that undermines the science. It is the science working exactly as it should. New observations refining earlier conclusions, uncertainty acknowledged, the answer getting sharper with each transit observed. But it illustrated something important about what Webb is doing in this system. The results are not simple. They are not clean. The TRAPPIST-1 star itself is active, producing stellar flares and surface spots that contaminate the planetary data. Distinguishing between a planet's atmospheric signal and the star's own variable output is an extraordinarily difficult technical challenge. Answers that seem clear from one set of observations can look different from another. The system is harder to read than it looked from Earth. This difficulty has a specific cause that astronomers knew about before Webb launched, and that has turned out to be even more significant than early models suggested. Red dwarf stars are not gentle hosts. Despite being dim and cool by stellar standards, they are magnetically active, producing frequent, powerful flares that blast their nearby planets with ultraviolet and X-ray radiation at intensities far beyond what Earth receives from our Sun. TRAPPIST-1 is no exception. The star flares regularly. Over billions of years, that radiation has interacted with whatever atmospheres the planets once had, potentially eroding them, ionizing the upper layers, driving gas molecules to escape velocities. The inner planets appear to have lost the battle. TRAPPIST-1b, C, and D seem to be stripped or near-stripped worlds. This is, if confirmed, a meaningful result for the broader search for life around red dwarfs, which make up roughly 3/4 of all stars in the Milky Way. If the habitable zones of red dwarfs tend to produce airless planets because the stars are too active, the number of potentially habitable worlds in the galaxy drops significantly. But the outer habitable zone planets, E, F, and G, have been receiving less radiation over their lifetimes. They sit further from the star's energetic output. They may have had time to retain or regenerate atmospheres. And in 2025, for the first time, Webb looked at the most important of them. TRAPPIST-1e is considered by most astronomers to be the single most compelling habitable world in the catalog of known exoplanets. It orbits directly within the star's habitable zone. Its size and estimated density are close to Earth's. Its equilibrium temperature, the temperature it would have if it absorbed and emitted radiation like a dark body, puts it in a range where liquid water could be stable on its surface. For Webb to look at TRAPPIST-1e was the scientific equivalent of finally opening the most anticipated envelope. Between mid and late 2023, Webb's NIRSpec instrument observed 4 transits of TRAPPIST-1e. 4 times the planet crossed in front of its star, allowing the telescope to collect light filtered through the planet's atmospheric edge. The analysis of those observations, published in September 2025, across multiple papers by teams at the University of St. Andrews, the University of Bristol, and collaborating institutions, produced an answer that was simultaneously encouraging and maddeningly inconclusive. The data was consistent with several possible scenarios. Scenario 1. TRAPPIST-1e has no atmosphere. A bare, rocky world in the habitable zone, like Mars in our own solar system. A world that once might have had conditions for life, but has since been stripped or simply never built a substantial atmosphere. Scenario 2. TRAPPIST-1e has a nitrogen-rich atmosphere with traces of methane. Similar in some ways to Saturn's moon Titan, cold, chemically complex, with an atmosphere that is not immediately hospitable to life as we know it, but that represents a world with active atmospheric chemistry. Scenario 3. TRAPPIST-1e has a global ocean covered by a layer of ice. An ocean world, like what many researchers suspect exists beneath the ice of Jupiter's moon Europa, potentially habitable in subsurface conditions even if the surface is frozen. All 3 scenarios are consistent with the data Webb collected from 4 transits. The stellar flares and surface spots of TRAPPIST-1 contaminate the spectrum at exactly the wavelengths that would otherwise allow the science team to choose between them. The telescope that was supposed to give us the answer has given us instead a narrower set of possibilities. It has not ruled life out. It has not confirmed it. It has told us with unprecedented precision that TRAPPIST-1e is worth looking at more. Here is what the results from the TRAPPIST-1 system tell us so far, and what they do not. The inner 3 planets, B, C, and D, appear inhospitable, not conclusively proven to be airless in every case, but trending toward worlds that stellar activity has stripped. This is not a trivial finding. It suggests that proximity to an active red dwarf is a serious challenge for atmospheric retention, a challenge that Earth has never had to face from our relatively quiet, middle-aged sun. The outer 3, E, F, and G, remain unresolved. TRAPPIST-1F and 1G have not yet been fully characterized by Webb. 1E has been observed, but not yet definitively categorized. The program continues. More observations are scheduled. More transits will be captured. More data will be processed. What Webb is doing in the TRAPPIST-1 system is not a single experiment. It is a long campaign, a multi-year effort to characterize 7 planets around a challenging active star. using a technique that is at the very edge of what current technology allows. Each set of observations narrows the possibilities. Each transit adds data. Each paper published refines the picture. The answer, whether any of these worlds has conditions that could support life, is coming. But it is coming slowly, the way answers to the hardest questions always do. Dr. Nestor Espinoza, the lead author of the 2025 TRAPPIST-1e paper, said something worth quoting directly. He noted that finding the planet has no atmosphere could be equally valuable to finding that it does. Because if Earth-like planets in habitable zones around red dwarfs consistently turn out to be airless, that tells us something profound about how rare life-supporting conditions are, about how special our own situation may be. A null result, in the right context, is still a result. There is a broader context for the TRAPPIST-1 observations that matters for the search for life across the galaxy. Red dwarf stars. Stars like TRAPPIST-1 make up approximately 75% of all the stars in the Milky Way. If red dwarfs are capable of hosting habitable, life-supporting planets, the number of potential biospheres in our galaxy is enormous. If they are not, if stellar activity consistently strips the atmospheres of close-in rocky planets, then the fraction of stars capable of hosting life drops dramatically. What Webb finds in TRAPPIST-1 will not definitively answer this question for the entire galaxy. 7 planets around one star is a sample of 1. But it is the best sample we have. It is the closest system with multiple habitable zone rocky planets. The answer Webb finds here, or even the refinement of the question Webb forces, will shape the direction of exoplanet science for the next decade. If TRAPPIST-1e turns out to have a nitrogen-methane atmosphere, the implications ripple outward immediately. Red dwarf habitable zones can sustain atmospheres. The galaxy's habitable real estate just expanded by orders of magnitude. The search for life intensifies with a clearer direction. If TRAPPIST-1e turns out to be bare rock, the implications are different. The stellar environment around red dwarfs may be consistently lethal to surface habitability. The search for life should focus on quieter stars, sun-like stars, like our own, even though they are rarer. The habitable real estate narrows. 1 planet, 40 light-years away. The outcome of Webb's staring contest with it matters not just for that planet, but for every assessment of how common life might be in the universe. Here is where the search stands in 2026. Webb's TRAPPIST-1 observation campaign is ongoing. The DREAMS program, Deep Reconnaissance of Exoplanet Atmospheres using Multi-Instrument Spectroscopy, continues to schedule and execute new observations of the system. More transits of TRAPPIST-1e are being captured. Observations of TRAPPIST-1f and 1g are in the pipeline. Meanwhile, the science community has been developing new techniques specifically to deal with the TRAPPIST-1 star's contaminating activity. Stellar contamination correction methods, ways of mathematically separating the planetary signal from the star's own variability, are improving. Each new transit observed helps calibrate these corrections. The TRAPPIST-1e question is expected to receive significantly more data over the next 2 to 3 years. By the time Webb's operational window begins to narrow, and the telescope is fully operational with enough fuel for at least another decade, the system's habitable zone planets should be substantially better characterized. TRAPPIST-1 is not going to give up its secrets easily or quickly. This is a star that challenges every measurement. A system that frustrates clean answers. A set of planets that sit at exactly the distance and size where the answer matters the most, and where the measurement is hardest. But the question is being asked. For the first time in human history, we are not just speculating about whether Earth-like planets and habitable zones have atmospheres. We are measuring them. With the actual light that passes through the actual edge of these actual worlds. Whatever the answer is, it exists, and Webb is reading it. There is a sentence that appeared in a NASA press release about the TRAPPIST-1e results in 2025. It read, "While an original atmosphere is unlikely, scientists are narrowing possibilities for a secondary atmosphere, even as Webb observations continue. Parse that sentence carefully. It contains a great deal. An original atmosphere, the one the planet may have been born with, is probably gone, lost to billions of years of stellar radiation. But a secondary atmosphere, one built up from volcanic outgassing, from impacts, from interior chemistry, remains possible. A world that was once stripped can rebuild. Earth itself has had multiple atmospheric compositions over its history, each one the product of different geological and biological processes. TRAPPIST-1e may be such a world, and TRAPPIST-1f and 1g, the two outermost habitable zone planets, receiving less radiation, older in their relationship with a star that may have quieted slightly over time, have not yet been characterized. They are still waiting, still transiting, still filtering the light of their star through whatever surrounds them, waiting for Webb to collect enough photons to tell the story. 40 light-years is not far by the standards of the universe. It is nothing, a step across a room in a building the size of a continent. It is close enough that the signals we are looking for are theoretically within reach of technology that exists right now in 2026. Whether they carry the signature of an atmosphere, whether that atmosphere contains chemistry that biology has touched, whether there is something on TRAPPIST-1e or F or G that breathes or photosynthesizes or simply exists in the complicated way that life does, we do not yet know. But James Webb is looking, every clear observation window, every transit, every photon, and when it finds the answer, whatever that answer is, it will be one of the most important sentences ever written in a scientific paper. Subscribe, because when that paper drops, we will cover it the same day.